Consider a system limited to 300 psi maximum pressure. Could this cylinder manipulate a 300-pound load? The answer is yes. Both the pressures necessary to extend and retract the cylinder with 300 pounds force are below the 300 psi maximum pressure limit. Could this system limited to 300 psi manipulate a 500-pound load? The answer is not really. The working pressure necessary to extend this cylinder is below the 300 psi maximum pressure limit. However, the working pressure necessary to retract the cylinder is above the 300 psi maximum pressure limit. One could extend the cylinder and apply a 500-pound load, but not retract it due to the increased working pressure necessary due to the smaller functional area provided by the rod end. Could this system limited to 300 psi manipulate an 800-pound load? The answer is no in both cases. Both extension and retraction working pressures are above this system's 300 psi maximum pressure limit. What is the maximum force that this cylinder can extend and retract given pressure is limited to 300 psi? Pascal's law states that the maximum extension force is the maximum pressure times the area of the cap end. The maximum extension force of this system limited to 300 psi is therefore approximately 622.2 pounds. Similarly, the maximum retraction force of this system is the maximum pressure times the smaller functional area of the rod end, which yields a maximum retraction force of approximately 441.8 pounds force. What if this process did necessitate the regular manipulation of 300-pound loads? In this case, a technician knowledgeable of Pascal's law tasked with upgrading this system has two available options at his or her disposal. Either they can increase the pressure or increase the area. Given force is equal to pressure times area, either manipulation or a combination of both could serve to increase the resultant force of our system. Consider the simple act of just adjusting the pressure relief valve so maximum pressure is no longer limited to 300 psi, but rather 600 or even 5,000 psi, thereby allowing this existing system to manipulate an 800-pound load with plenty of room to spare. This solution is not without its complications, though. Can the existing motor-driven pump provide sufficient flow at the increased pressure requirements? Can the existing hoses and fittings handle the increased pressure, especially when pegged at the ridiculous limit of 5,000 psi? If not, consider keeping the maximum pressure limited to 300 psi and simply swapping out the existing cylinder with one with increased functional area. Consider a cylinder with a 2.5-inch diameter cap end and the same 7/8 inch diameter rod. The cap end area for this larger cylinder now represents approximately 4.9 square inches of functional area, and the rod end represents approximately 4.3 square inches of functional area. Given the larger functional area for both cap end and rod end, how does this affect working pressure for extension and retraction when handling an 800-pound load? Pressure at extension is equal to the force divided by the functional area of the cap end. Substituting in the necessary values, we find this larger cylinder necessitates a working pressure of only 163 psi. Similarly, we find this larger cylinder necessitates a working pressure of only 185.7 psi to retract it. The larger cylinder, therefore, allows us to manipulate the 800-pound load without exceeding the 300 psi maximum pressure limit. Consider the increased load range capable of being handled by this larger cylinder. Given force equals pressure times area, when working pressure is pegging our previous limit of 300 psi, the larger cylinder can extend using the cap end area with up to 1,472.6 pounds force and retract using the rod end area with approximately 1,292.2 pounds force. Again, proving the larger cylinder has more than sufficient force to toss around the 800-pound load like a hacky sack in a liberal arts college parking lot. The solution is not without its complications, though. Note a larger cylinder does provide increased functional area. However, it similarly increases the volume of space the pump must fill to fully extend and retract the cylinder. The existing motor-driven pump may not provide sufficient flow to actuate the larger volume cylinder within the desired time period. This is to suggest that safety, effectiveness, costs, benefits, and the cold hard limits of time and money must be taken into consideration. Before we wrap this lecture up, let's do one more illustrated example problem. Given a huge cylinder with a 6-inch diameter cap and a 2-inch diameter rod, Determine the working pressure for both extension and retraction, given the cylinder is tasked with pushing and pulling 5,000-pound containers on and off barges. Additionally, determine the maximum extension and retraction force of the system, given maximum pressure is limited to, let's say, 400 psi. Finally, can this system as currently implemented push and pull 2 containers on or off at once? If not, what modifications might be necessary to do so? By all means, pause the lecture and take your best shot at this. Note, I did not give you a detailed roadmap for this illustrated example problem. It's up to you to pick the best route to the solutions. If you perform the calculations, you should have obtained the following results. The cap end area is 28.2743 square inches. The area of the rod end is approximately 25.1327 square inches. Note, area calculations are often the first stop one makes on a road trip to Solution Town. This isn't always the case, and watch out for occasions when an especially devious instructor tricks you into performing unnecessary calculations. However, area calculations are almost as essential as filling up your car with gas and making sure your car has 4 wheels when it comes to force, pressure, and area calculations. Pascal's Law shows that to extend with 5,000 pounds of force using the larger cap end area necessitates a working pressure of approximately 176.8 psi. Similarly, Pascal's Law shows that to retract with 5,000 pounds of force using the smaller rod end area necessitates a working pressure of approximately 198.9 psi. Given the system is limited to 400 psi maximum, Pascal's Law shows that this system would be able to produce a maximum extension force of approximately 11,309.7 pounds force. Similarly, Pascal's Law shows that this system would be able to produce a maximum retraction force of approximately 10,053.1 pound force. So the answer to our final question is a definitive maybe. Given each container represents a 5,000 pound load, 2 of them together would represent a 10,000 pound load. The system as currently implemented could theoretically push 2 containers onto the barge simultaneously. However, I sincerely doubt it would be able to pull 2 containers off the barge simultaneously because the force of retraction at this pressure limit is only slightly over the requirement. Accounting for inefficiencies due to leaks, friction, unintended pressure drops, and any play between the mechanically coupled loads, I sincerely doubt this system as currently implemented would be able to do this in the real world. This is to suggest that Pascal's Law calculations represent theoretical maximums only. Real-world complications must be taken into account. Don't be the person that thinks it's going to work out perfectly and be totally shocked when it doesn't. Long story short, when you gotta kill a lion, a spear might do the job, but a high-power rifle has a significantly greater chance of success. Taking into account these realities, a technician presented with a system necessitating more force has 2 options available: either increase maximum pressure or increase functional area. Both options serve to increase force. However, due to pressure limits imposed by the existing fittings and monetary and time constraints, let's pretend neither of these upgraded modifications are feasible. A third option exists that requires minimal modifications to our system and a little out of the container thinking. Consider relocating the offloading cylinder from the dock onto the barge during an offload, such that when the cylinder extends, it pushes 2 containers onto the dock simultaneously. Aha! Given the same cylinder and the same maximum pressure limit, this relocated system can now offload from barge to dock by extending with a maximum of 11,309.7 pounds force, rather than retracting with a maximum of 10,053.1 pounds force. During offload, the system would be mounted onto the boat tied to the dock so it is capable of pushing 2 containers off the boat onto the dock by extending. During onload, the system could be remounted on the dock so it is capable of pushing 2 containers onto the boat by likewise extending. As this tricky solution demonstrates, the act of extending or retracting a cylinder can mean 2 totally different things when it comes to the desired task. Doubly so for systems including additional mechanical linkages. Keep in mind, the previous illustrated example problems featured cylinders laterally pushing and pulling fully supported loads, not lifting or lowering loads against the force of gravity. Consider these two different orientations used to lift and lower loads. To lift load A, pressurized flow must enter the cap end and cylinder A must extend the rod. In contrast, lifting load B requires pressurized flow to enter the rod end and retract the rod to lift load B. This is to again suggest that the act of extending or retracting a cylinder can mean two totally different things when it comes to the desired task pending mounting orientation. Cylinder A lifts on extend. Cylinder B lifts on retract. Given identical loads and identical cylinders, which orientation requires more pressure to lift the load? If you said cylinder B, you're correct. The pressure differential to lift the same load on retraction is because of the fundamental area imbalance between the cap end and rod end area. Again, you must understand how a double-acting cylinder is constructed and how the functional area affects working pressure. As a further concern for lifted loads, consider the influence of gravity on these two configurations. Lifting the load, either through extension or retraction against the force of gravity, is similar to our previous illustrated example problems featuring fully supported, laterally manipulated loads. However, the act of lowering the loads, either through retraction or extension, presents us with an overrunning load scenario and a whole lot of problems. The same thing goes for tipping and tilting applications where past a certain point, the load becomes negative. Given cylinder A lowers on retraction, and given little pressure is present in the cap end to slow the descent of the lifted or tilted object, the lifted load in cylinder would crash to the limits of travel, and perhaps beyond. Similarly, if cylinder B lowers on extension, given little pressure is present on the rod end to slow the descent of the lifted object, the load in cylinder would crash to the limits of travel and perhaps beyond. Later lectures will examine flow control methods and counterbalance valves used to control the descent of a lifted object. Long story short, both methods serve to restrict or control fluid from leaving the supporting end such that pressurized fluid is always available to resist the overrunning nature of the lowering load. Alright, this about wraps up our brief introduction to Pascal's Law. In conclusion, this lecture took a brief look at the relationship between working pressure, functional area, and force, known as Pascal's Law. Additionally, we examined applications of Pascal's Law, including force multiplication and scenarios involving extending and retracting cylinders. Finally, we discussed maximum pressure limitations and how different cylinder orientations and mounting methods may influence the force, pressure, and resultant mechanical movement. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.